The difference between these, the idea of microstates versus macrostates, they're both descriptions of some system, typically a fairly complicated system. But what exactly is the difference between them? What do we mean by a microstate versus a macrostate? Have you seen any definitions about that so far, or what they actually mean? Sort of smaller. It's not so much that we're talking about like a physically smaller thing. It's more looking at it on a closer level, looking at it in more finer detail, I guess you might say. The macrostates are generally a broad overall description of the whole system. So sort of a big picture look, usually without too much detail. Whereas a microstate is more of I mean, it's still talking about the whole system, but it's looking at listing out the individual details of what's going on. So I'm going to say a detailed list of the individual behavior of each piece of the system. So if you're describing the whole system, but not really looking at the finer details, if you're just doing a general description of what the whole thing looks like, that's probably a macrostate. If you're listing out the individual behavior of each piece of the system, that's definitely a microstate. And technically any microstate also counts as a macrostate. But usually we're talking about a macrostate that includes many microstates. And I think this is probably going to be easiest to see with some examples. Like for example, let's say we're talking about maybe rolling 2 dice. And to keep the numbers simple, let's say they are 4-sided dice. So you've got a tetrahedron marked with a 1 on one corner, a 2 on one corner, 3 on one corner, and a 4 on one corner. So you roll this tetrahedron. If whatever the top point is labeled, that's what you just rolled. So let's say you've got 2 4-sided dice and you're rolling them. Let's say this is a game where you take 2 4-sided dice, roll them, and then add the numbers together, and that's your score or something like that. So what are some of the possible results you could get from rolling 2 4-sided dice and adding them together? What possible values could you get by rolling 2 4-sided dice and adding them up? Yeah, anywhere from, well, how would you get 1 though? Is it possible to get 1 by rolling 2 dice? Yeah, going to be 2 through 8. So those would be the macrostates. You could roll the dice and say, I rolled a 5. And that wouldn't necessarily give any specific information about the individual behavior of each one of those dice. It's just telling you the total of the whole system. So an example of a macrostate in that system would be something like the dice add up to 5. So this would be an example of a macrostate. It's telling you a general description of the whole system without going into much detail about the individual pieces. But what would be an example of a microstate? How would you describe the behavior of the individual pieces here? Yeah, any number 1 through 4 on each die. So we'd say the first die rolls a certain number and the second die rolls a certain number. So a microstate in this context would be a listing of two numbers, and order matters here, describing what each die says. So for instance, and since it's two numbers, we could write this as an ordered pair. We could say, for instance, what's one way you could have the dice add up to 5? Yeah, you could have 2 and 3. Or what else? 1 and 4. Any other pairs that add up to 5? Yeah, 3 and 2 would count as a different one because we're talking about two physically different objects, two different dice. It might help to imagine them as different colors. Like let's say you've got a red die and a green die. You roll them, you might have a red 2 and a green 3, or a green 2 and a red 3. That would be listing it in a different order. Those still add up to 5, but since they're two physically different objects, order matters. And likewise, 4 and 1. And I think that's it. We can't really have like 5 and 0 because those aren't numbers on the dice. So it looks like there's 4 different ways that you could roll a 5 in total. So all 4 of these microstates are associated with this macrostate. There's 4 different microstates, 4 different ways for this macrostate to happen. Any questions on that so far? What if instead our macrostate was, let's say, the dice add up to 8? What microstates would be associated with the dice adding up to 8? The dice only go up to 4, though. You can't roll a 7 and a 1 because they're 4-sided dice. So what are two numbers from 1 to 4 that would add up to 8? Yeah, 4, 4 is the only way to do it, right? You can't have 3 and 5 because 5 isn't listed on these dice. So 4, 4. And in this case, you can't really swap the order because red is 4 and green is 4 is the same as green is 4 and red is 4. It's still 4 and 4. So there's only one microstate associated with this macrostate. And what does that suggest? If there's 4 different ways to roll a 5, but there's only one way to roll an 8, what does that tell you about rolling a 5 versus rolling an 8? Yeah, there's a greater chance of getting a 5. This is really, right, it's more likely. This is the foundation of probability. Probability is really all about how many microstates are associated with a given macrostate. A macrostate is more likely to happen if it's associated with more microstates. Because the foundation of all this is that we're assuming that each one of these microstates is equally likely. Rolling a 2 and a 3 is exactly as likely as rolling a 4 and a 4. But since there's more different ways you could get a 5, you would essentially be adding up these probabilities. There's a little tiny probability of each one of these happening. But there's 4 times that much little bit of probability to get a 5 because there's 4 ways that can happen. Any questions on that so far? And we can also describe macrostates in other ways. Macrostate doesn't have to be what the dice add up to. We could also have something like maybe the dice roll doubles. If we say, for instance, both dice are the same. Same number on both dice. In other words, we roll doubles. That would count, that would be called a macrostate because it's a broad general description of the whole system without giving too much detail. But we can say what microstates would be associated with the same number on both dice. Yeah, you could have 1, 1, or 2, 2, or 3, 3, or 4, 4, and that's it, because these only go up to 4. Yeah, in general, n comma n, where n can be 1, 2, 3, or 4. So there's 4 different microstates associated with the state, same number on both dice. And so when we say state, we usually mean macrostate. Sometimes they actually spell out macrostate. Sometimes they just call it a state. But that means 4 microstates are associated with same number on both dice. What does that suggest? How does that compare to, for instance, rolling a 5? Yeah, they're equally likely. The probability, if you roll those 2 4-sided dice, you have the same probability of rolling doubles as you have of rolling a 5, because they have the same number of microstates. So that means they have the same probability. Again, probability is ultimately just a measure of how many microstates. More microstates mean associated with that macrostate means that that macrostate is more likely to happen. And you can write all of these probabilities as fractions. In general, probability of something happening is going to be the number of microstates associated with that thing divided by the total number of macrostates. We're looking at what fraction of the total possibility space is taken up by that macrostate. And how would we figure out the total number of possible microstates? In this case, where we're rolling 2 4-sided dice. Like we've listed out some of them, 1, 1, 2, 2, 3, 3, 4, 4, 2, 3, 1, 4. How would we be able to tell how many there really are in total? In this case, it's a small enough system, we could probably just list out all of them, right? I mean, there's only 4 possibilities for the first die and 4 possibilities for the second die. But a useful way of checking how many there should be in total, how many microstates to expect, you could think of this as 2 events. Yeah, in this case, x to the n should work because the 2 events are equal. Like there's no difference between the 2 dice. In general, I would say, imagine you're rolling 1 die as an event. If you roll these dice one at a time, because it doesn't really matter what time you roll them. They don't have to be both rolled at the same time. You roll the first die, and then you roll the second die. You roll the first die, how many possible outcomes are there for that 1 die? Yeah, 4 possibilities for the first die. And the second die is completely independent. These dice don't influence each other at all. So the second die, being exactly the same, also has 4 possibilities. And in general, these don't have to be the same number, by the way. We could be rolling, for instance, a 6-sided die and a 10-sided die. So it'd be 6 and 10, for instance. Alternatively, maybe the events influence each other. Like, let's say instead of rolling 2 dice that are independent, let's say we have a deck of cards labeled 1 through 4. We draw 1 number from the deck, and then we draw a second one. The second one has fewer possibilities because we've already pulled 1 card out of the deck. So maybe for the first card we pull from the deck, there's 4 options. But the second card, there would only be 3 options left because we've already removed 1. So it would be 4 and 3 instead of 4 and 4. So whether the events are independent from each other or whether they're influencing each other makes a big difference here. In this case, though, both dice are completely independent. They don't influence each other. So it's just 4 and separately another 4. What could we do with those 4s if we wanted to figure out the total number of possible microstates? The total number of possible combinations. Not 4 to the 4th power in this case. A very useful way to visualize this is, at least if you only have 2 events. If you've just got 2 events happening, it's very convenient to draw out a grid. If you imagine that, like, the first die could be 1, 2, 3, or 4. If you just list out the possibilities. 4 possibilities for the first event. And then the second event, let's draw on the other axis. The second die could be 1, 2, 3, or 4. And then if you think of this as, I guess you might say an addition table, like a multiplication table, but for addition instead. We're listing out all the possible combinations. For example, if you roll a 1 and a 1, you add those up, you get 2. Roll a 2 and a 1, you add those up, you get 3. 3 and a 1 is 4, 4 and a 1 is 5. And we could keep filling these in. 1 and 2, 2 and 2, 3 and 2, 4 and 2, 1 plus 3, 2 plus 3, and so on. This is just going to keep increasing. So this lists out all the possibilities. How many possibilities are there here? How many microstates? Yeah, 16. How do you get that from the 4 and the 4? Right, we're just multiplying. You could even think of this as like an area. You've got a width of 4, a height of 4, so you multiply 4 times 4 to get an area of 16. So we really are just multiplying. In general, if you have two independent events, two events that are not influencing each other at all, then you can figure out the number of possibilities for the first event, the number of the possibilities for the second event, and just multiply them. So there's 16 microstates possible here. And we could group those together. A chart like this makes it very easy to see how many of each macrostate there is. Because what we've listed in these boxes is categories of microstates. For instance, rolling a 5, it looks like a 5 is going to be the most likely of these numerical microstates because there's more 5s than anything else here. So rolling a 5, probability of a 5, how would you calculate that probability? If we want to write probability as a fraction. Yeah, 1/4. And before you reduce it, you could write it as there's 4 5s, and there's 16 possible microstates altogether. So in general, a probability of some macrostate happening is the number of microstates associated with that macrostate divided by the total number of possible microstates. So there's 16 microstates possible here, 16 possible combinations of 1 and 1 or 2 and 2 or whatever. Of those, only 4 of them add up to 5. So 4 microstates of the type we want divided by 16 possible microstates equals 1/4 or 0.25 or 25%. Those are all valid ways of writing the probability. It's often a good idea to leave it in the unreduced form though, 4 out of 16 in this case, so that you can compare it to other probabilities that are out of 16. For instance, the probability of rolling a 3. There's only 2 possible microstates that are associated with that. So the probability of rolling a 3 would be 2 out of 16, which is only half as much as the probability of rolling a 5. So this makes for a very convenient way of comparing probabilities. The probability of something happening is all about how many microstates are associated with that thing as a fraction of the total number of microstates. Any questions on that so far? And the main way this is going to apply to thermodynamics is that the number of microstates is used in calculating another quantity called entropy. Entropy is basically just a measure of the number of microstates. Number of microstates, by the way, we usually call capital omega. So this capital Greek letter omega means the number of microstates. And entropy is defined in terms of microstates. Entropy, usually written as a capital S, is the number of microstates. But the problem is the number of microstates tends to be enormous in thermodynamic systems. Like in this case, where we're just rolling one die and rolling another die. But if you use these as metaphors for molecules, like let's say you've got a molecule, instead of a die that can show a 1, 2, 3, or 4, let's say you've got a molecule that can have various different amounts of energy instead of numbers showing. Like imagine the energy of one molecule is the number shown on the die. But there's lots of different amounts of energy the molecule can have. And also, we're probably not dealing with 2 molecules. How many molecules would we typically be dealing with? What would be a reasonable number of molecules to use in a sample? Yeah, Avogadro's number. So instead of having 4 to the power of 2, because you've got 2 dice, instead of having something to the power of 2, because you've got 2 dice, you'd have something to the power of Avogadro's number, because you'd have a mole of molecules, as one example. Maybe you've got 3 moles, so you'd have something to the power of 3 times Avogadro's number. But you get these enormous exponents. These exponent, typically the exponent is going to be the number of things in the system, and the base is how many options there are for each of those things. So in typical systems of like a sample of gas, you've got ludicrously large exponents. So the number of microstates is so enormous that it would be inconvenient to do any calculations with that directly. So we're going to trim it down to size by using a very convenient operation. What's one mathematical operation that takes ludicrously large numbers and trims them down to a more reasonable size? I guess there's a lot of operations that fit that description, but the one we're going to use here is the logarithm. To define entropy, it's not just the number of microstates, it's the natural logarithm, ln, of the number of microstates. And the reason we specifically use a logarithm has to do with what we can do with exponents in logarithms. If you've got something ludicrous like something to the power of Avogadro's number, this is just going to be a ludicrously large number. But if you take the logarithm of it, what can you do with an exponent inside a logarithm? Yeah, you can bring that out as a multiplier. And of course, it doesn't have to be in the front because multiplication is commutative. We could write that instead as logarithm of x times the exponent. But the important thing is that a logarithm can turn an exponent inside the logarithm into a multiplier outside the logarithm. And multiplying by Avogadro's number is still pretty big, but it's nowhere near as inconvenient as raising something to the power of Avogadro's number. So the main reason why we define the logarithm is why we define entropy in terms of logarithm of the number of microstates is that number of microstates tends to have absurdly large exponents. But the logarithm allows us to extract that exponent as a multiplier, which is much easier to deal with. Another important thing about using the logarithm here is how it deals with division, because in many situations we end up with ratios of microstates, number of microstates available in one situation compared to number of microstates available in some other situation. If you've got logarithm of, let's say, A divided by B, how could you split that up? Division inside a logarithm can be split up into, subtraction. You get logarithm of A on its own minus logarithm of B on its own. And the reason this is really useful is if the ratio happens to be initial and final values of something, like let's say this is specifically the ratio of the final number of microstates or after some process happens, divided by the initial number of microstates before some process happens. Then we're going to have omega final minus omega initial inside logarithms. And what do we call final minus initial? Right, that's a delta. It's not delta omega, but it is delta logarithm of omega. Delta logarithm of omega. So we can find a delta entropy based on the ratio of the number of microstates. This is another big advantage of using a logarithm here, that it turns a ratio into a delta. It turns a ratio into a subtractive difference. And that's very useful because we often have ratios of microstates. Usually when we make some change to the system, the number of microstates gets multiplied by something or divided by something. So it often makes sense to talk about microstates in terms of multiplication and division. But the logarithm turns multiplication and division into addition and subtraction, which is very convenient for calling things delta entropy, delta S. So that's really the main reason why we use a logarithm here. Also, in order to deal with the Avogadro's number that often gets pulled out from the exponent as a multiplier, we also put in a times Boltzmann's constant here. That way, whatever enormous multiplier we pull out gets multiplied by a very small number and trims it down to a more reasonable size. This also gives us the units of joules per Kelvin, because Boltzmann's constant is measured in joules per Kelvin. And having those units makes it appropriate for dealing with other situations as well. Joules per Kelvin is the units of measurement we want for entropy. So that's the main idea of entropy here, that we're taking the number of microstates, how many ways there are for something to happen in terms of listing out the individual details, taking the logarithm of that, natural logarithm specifically, logarithm base E, and then multiplying that by Boltzmann's constant. That's what entropy means. It's just a measure, a modified measure of how many microstates there are, how many ways a system can exist. Any questions on that so far? All right, and I think we're going to be looking at both entropy and probability in a lot more detail next week as well. But for now, I'd like to spend some time on the pressure volume graphs too, because I think it's going to be a good idea to just go over at least one example of that in terms of what are the actual calculations going to look like. Let's say we are dealing with a let's say we have a diatomic gas. Specifically, let's say 3 moles of, actually, let's not say 3 moles. Let's say we don't know the number of moles. We've got a diatomic gas. And we're going to be messing around with its pressure and volume. And therefore, what else? What else is going to change if you change the pressure and volume around? Yeah, the temperature, because we can always go back to the ideal gas law, pressure, volume, and temperature related to each other. And let's say we have some specific values of those. Let's say the volume and the pressure are both changing in ways we can measure. Let's say we've got the correct laboratory equipment for measuring pressure, a barometer, and for measuring volume. Let's say it's just in a cylindrical case with a piston that can move around. So you can use geometry and rulers to measure the volume of the gas. And let's say it's changing from, let's say it's going from 2 cubic meters to 8 cubic meters. And also, let's say the pressure is changing between 200,000 pascals and 600,000 pascals. So pascals is the usual unit of pressure. Let me make a note of this on the side. Pressure is measured in units called pascals. 1 pascal means 1 Newton per square meter. Because force is all about pressure, pressure is all about force distributed over an area. If you're pushing on a wall, you're applying a force, but that force is spread out over the area of your handprints. So the pressure you're applying is the force you're applying divided by the area. Pressure is force over area. Force is measured in newtons, area is measured in square meters. That newtons per square meter is also called pascals. But another convenient way to write that, if we multiply the top and bottom by meters, what do you get if you multiply newtons times meters? Yeah, that's joules. In the sense of work, for instance, force times distance is work, which is a transfer of energy. So the units of force times the units of distance have to equal the units of energy, joules. So joules over, and then meters squared times meters, meters cubed. So pascals can be written as newtons per square meter or joules per cubic meter. This particular chart is listed in kilopascals. So 1 kilopascal will just have 1,000. Kilo means 1,000, so that's 1,000 joules per cubic meter. So we can use that as a conversion factor if we need to. We can make that substitution. But let's say we have a transition here. Let's say we have a gas that starts off at, let's say, low pressure and high volume. And let's say it ends up at low volume and high pressure. And just knowing those 2 points alone is not enough information, because there might be, there's many different ways that it could go. You could go along a straight line path, or you could go straight up and then straight to the left, or straight to the left and then straight up, or on any sort of curve. There are many different paths that will take you from initial to final. But let's say we're just focusing on one of them. Let's say we're taking a straight line path. So if we are taking a straight line journey, transition from initial to final, so we are doing something to the gas to shrink its volume, we're compressing it, and also increasing the pressure. A nonlinear path, I would guess that if it's a nonlinear path, if it's curved, they would probably just give you the relevant information. But more formally, you would usually use an integral, like if you actually know the function. But let's see if we can figure out information just based on this. I think we are going to need one more piece of information. Well, do we need? I don't know. Let's see what we can do with just this information. Then we can throw in more information if we need to. Let's say we want to figure out all the information we can about this process. For instance, in order to do this, how would you actually make this happen? If you want to make this gas get compressed, what do you have to do to it? Yeah, you've got to do work to it. In general, if you want to compress a gas, you have to do work to it. Whereas if you wanted to allow the gas to expand, work would be leaving the system as the gas, like let's say the gas expands and pushes the piston up. That means the gas is doing work to raise the piston. So if the gas expands, work is leaving the system. So we treat work as negative. If the gas is being compressed, you're doing work to the system. So we treat work as positive. Work is entering the gas. And in this case, we're compressing the gas. Volume decreasing means that work is being added to the system. So we would say work is positive. Work is entering the system. And if work is involved, work is just a transfer of energy. So we should be looking into the idea of conservation of energy. And as usual, we can use conservation. Delta energy equals work plus heat. In the context of thermodynamics, we usually use the variable U for energy, capital U. And this capital U here is specifically talking about internal energy. And what do we mean by internal energy? What kinds of energy count as internal, like contained within the object? This one's not actually a closed system because we are doing work and presumably heat might be entering or leaving as well. But yeah, thermal energy and bond energy. When we're talking about internal energy, we're talking about the types of energy that are in the object itself, as opposed to in relation to something else. Like for instance, potential energy of gravity. An object has potential energy of gravity because of its interaction with the planet itself. It's not just energy that the object has in its own right. Likewise, kinetic energy. If an object is moving, it has kinetic energy because it is moving past something else, like moving along the ground or moving relative to some other reference frame. Kinetic energy is not really an energy that the object has within itself, unless you're talking about kinetic energy of the individual molecules, but that's really more about thermal energy, as you say. So internal energy incorporates thermal energy and also bond energy, because that's the energy that the molecules have in relation to each other inside the object. And also some other energies as well. For instance, chemical energy, if there's a chemical reaction going on, and atomic energy, the energy inside the nucleus that's released during nuclear fission and fusion. So internal energy includes all of these, but we're not talking so much about the amount of energy it has, we're talking about the change in energy. And if we just have a gas that we're compressing, what's presumably the only one of these that's actually going to be changing? Presumably thermal energy, yeah. The gas might increase or decrease its temperature as a result of the ideal gas law. Changing the pressure and volume can cause changes in the temperature. But we're not going through any phase changes. We're assuming this is a gas the whole time. So the bond energy is not changing. The gas might have chemical energy. It is diatomic, so it's going to involve some chemical bonds. But we're assuming there's no chemical reactions happening. So the chemical energy is not changing. And likewise, there is lots of energy packed inside the nuclei of the atoms, but we're not doing any splitting or merging of nuclei. We're not having any nuclear fission or fusion, so that the atomic energy is not changing. The only part of this that's changing is the thermal energy. So for our practical purposes, delta U is delta E thermal. That's the only one that's changing in this context. So that's the usual conservation of energy principle. The delta energy of the system, in this case, just delta E thermal, is caused by the work and heat done to the system, or in entering or leaving the system. In the context of thermodynamics, we usually call this the first law of thermodynamics. Which is really just a fancy word, a fancy way of saying conservation of energy. But the first law of thermodynamics is conservation of energy, specifically applied to internal energy. So we know that work is being done, energy might be changing, maybe the temperature is changing, and there might be heat entering or leaving. So ideally, we'd like to be able to figure out all three of these. How much work is entering, how much heat is entering or leaving, we don't really know yet, and how much is the thermal energy of the system changing as a result. And it turns out we can get all three of these based just on this graph. So let's start with that. For instance, internal energy, the thermal energy of the system. Do you have any formulas for thermal energy that might depend on pressure and volume? And keep in mind, this is an ideal, we are assuming this is a gas, an ideal gas. So you can always use the ideal gas law in these cases. We've got information about pressure and volume, P and V, but we can always use the ideal gas law to relate that to nRT. Do you know of any formulas for thermal energy that use N times R times T? Yeah, this one really convenient one we built a little while ago, N times R times T times number of modes over 2. That is a formula that will work for thermal energy based on the microscopic behavior of the individual mode or individual particles. And since this is an ideal gas, because this formula so far works for any substance, but because this is a gas, we can also replace nRT with PV. So pressure times volume times number of modes over 2. And so that tells us a way to find the thermal energy just based on the pressure volume graph. So let's try that. Or actually, we should apply a delta here. Delta E thermal equals, and since pressure and volume could both be changing, yeah, this one only works for a gas. Because the only reason we're able to replace nRT with PV is because of the ideal gas law, which only applies to gases. And really, it only applies to certain well-behaved gases. But it's a good approximation even for non-ideal gases. If we apply a delta to this, the fact that pressure and volume could both be changing means we should enclose them both in the delta. This is essentially pressure final times volume final minus pressure initial times volume initial times number of modes over 2. Number of modes can change if we're talking about changing the temperature so much that we're activating frozen out modes, but let's assume the temperature is not changing that much here, assuming the number of modes is constant. We should be able to calculate this, assuming this diatomic gas, let's say this diatomic gas is close to room temperature the whole time. How many modes would you expect per particle? Yeah, 5 modes per particle. So we could fill that in. We should be able to calculate the change in thermal energy by just subtracting final values minus initial values. So if we actually write that out, we've got P final V final minus P initial V initial. So final pressure times volume, 600 kilopascals times 2 cubic meters minus, and then the initial pressure and volume, 200 kilopascals times 8 cubic meters. So that's the delta pressure times volume, delta of that whole thing, times number of modes over 2. This expression should tell us how much the thermal energy changes. So we've got 600 times 2 is 1200, 200 times 8 is 1600, 1200 minus 600 would, or 1600 would be negative 400. And as for the units, I mentioned earlier pascals times cubic meters is joules. We've also got kilos, so that's kilojoules times 5/2. And then 400 divided by 2 is 200, times 5 would be 1,000. So we get negative 1,000 kilojoules as the delta E thermal. So that means during this process, as we go from initial to final, the gas is losing 1,000 kilojoules of thermal energy. Any questions on that so far? So it looks like we now have delta U. So work plus heat has to add up to negative 1,000. But can we find either one of these from the graph? Yeah, how would you find work based on a graph like this? Exactly, area underneath that path. And that's all the way down to the axis itself. So that area of that trapezoid is going to be the work done. And it might be convenient in this case to split it up into a rectangle and a triangle. So find the area of the rectangle just using base times height, and the area of the triangle, base times this height divided by 2. That tells you the total amount of work done. And note that when you calculate that, you're going to be multiplying a number of cubic meters times a number of kilopascals. So that's also going to be kilojoules. So that tells you the work done We know it's positive because you're compressing it. And if you know the delta U and the work, you can solve for Q as well. So you can get all three of these. Delta U based on initial and final values and the delta U thermal formula. Work based on area under the path all the way down to the axis. And then Q is the only unknown left, so you can solve for that. Any other questions on that process? Yeah, exactly. The area, I mean, formally, you would write this as work equals negative integral of pressure d volume from initial volume to final volume. So this would be the formal way to write it, in the sense that you're integrating, if you think of pressure as a function of volume, you're integrating that function to figure out the area under the curve all the way down to the axis from some initial volume to final volume. And the negative sign is just to take care of the idea that if the volume decreases, you're increasing the energy by adding work to the system. So the negative takes that into account. But ultimately, the integral just means the area under the curve on the graph. So the area under the curve on the graph is the work done to the gas or by the gas. And if you have this function like written out as a mathematical expression, you can integrate it. If not, you can use geometry to find the area under the curve. And the geometrical approach works really well as long as the curve is a straight line. You can always split it up into rectangles and triangles. If it's a curved path, presumably either they give you a function that you can integrate or they just give you the area under the curve right away. Or alternatively, maybe give you enough other information that you can solve for it. All right, try this process on P delta V. That would be specifically if it's a flat line. Because if the curve was just flat, horizontal, then the area under the curve would just be a rectangle. So that would be the pressure times the change in volume. And that's basically what you get if P is constant. If the pressure is constant, you can pull pressure out of the integral. And integral dV is just the change in V. So if the pressure is constant, otherwise known as an isobaric system, or an isobaric process, no change in pressure, then this integral just turns into negative P times delta V. But if the pressure is changing, then integral is the way to go. But either way, it's the same thing. You're just looking for the area under the curve. This is just a simplified version of the integral under certain specific circumstances. All right, I've got to get going, but try this same process on your F&T problems, or even just make up examples. Choose some starting values and ending values of pressure and volume, and try going through this same process. Find delta energy based on initial and final values, find work based on area under the curve, and then heat is whatever's left over algebraically. So give that a try, and I will see you next time. You're welcome.